Okay, let's unpack this. Today, we are diving into, well, really the hidden infrastructure of the digital age. We're stepping into a foundational territory that underpins almost everything complex in our modern world, from your social life to the way Amazon delivers a package. We are talking about the language of graphs. You've given us a stack of sources that establish the absolute fundamentals, and our mission is clear. We need to turn what often looks like impenetrable abstract mathematical notation into crystal clear visual and computational intuition for you.
It's a crucial mission. Graph theory is perhaps the single most versatile and powerful tool in computational thinking. It's the framework you use when you realize the world isn't about geometry, it's about relationships. If you want to know how information flows, how structure is maintained, or how optimization algorithms actually operate inside a machine, you have to start here. By the end of this deep dive, you'll have the core vocabulary to read the blueprint of complexity itself.
And we begin with the central analogy that frames this entire field. Graph theory is often called the Swiss Army knife of computer science. Why? Why that specific analogy?
That analogy captures the essence perfectly. It's not specialized, it's universally applicable. We're talking about a toolkit for analyzing relationships no matter what the context is.
Right, so let's ground this in reality, because this isn't abstract math just floating out in space.
Hmm.
Think about your daily interactions. When you open a professional social network, LinkedIn for instance, you are a unit and your connections are links. That entire system is a graph. The nodes are the people, and the edges are the professional relationships.
And the computational tasks are massive. You plug an address into your navigation system, your GPS. That system isn't running simple geometry calculations, it's querying a massive graph. The roads are the edges, but crucially, those edges have weights like time or distance. The intersections are the nodes. Graph algorithms, like Dijkstra's, are running constantly in the background, calculating the shortest, fastest, or cheapest route through that highly interconnected network.
Or take logistics. Every time a package moves from a warehouse to a sorting facility to your doorstep, that entire supply chain is modeled as a graph to ensure maximum efficiency. And as you mentioned, even the physical world of technology relies on it.
Absolutely. The design of a microchip, routing electrical signals through a circuit board, or even optimizing server traffic within a data center. All those connectivity and flow problems are fundamentally modeled as graphs. Every complex system, from vast biological networks like protein interactions to infrastructure like power grids, it can all be simplified and analyzed using this precise language. It really is the foundational language of system structure.
So let's formalize that language.
Yeah.
We need the fundamental, untouchable definition that defines any graph at all. What is the core structure we're talking about?
Okay, so a graph dollar is defined as a pair. A dollar full of dollars is the set of vertices, which we usually just call nodes. These are the actors, the locations, the points of interest. And andollars is the set of edges. These are the connections, the relationships, the links between those nodes.
The textbooks often define the edge set 81, using formal set theory, saying $80 is a subset of all two-element subsets of $5. That sounds terrifying to a beginner. What is the simple functional meaning of that?
Yeah, that definition is just there to guarantee simplicity and organization. The practical idea is simple. Every edge is defined by the pair of unique nodes it connects. The fact that it's a set of two elements, not an ordered pair, means the connection from node A to node B is structurally identical to the connection from node B to node A.
So no direction.
Exactly. We're just talking about pairings of neighbors. It guarantees that every connection has a start and an end, and crucially, for now, there's no implicit directionality.
That clarity is important. Now, let's lock down some essential vocabulary that flows right out of that full pair, defining relationship and position. We use the terms adjacency and incidence.
Adjacency is the relationship between two nodes. So nodes in all our dollars are adjacent if and only if there is an edge directly connecting them. We call them neighbors. It's a peer-to-peer relationship. If you and I are adjacent, we are one step away from each other.
And incidence focuses on the connection to the edge itself.
Exactly. Incidence describes the relationship between a node and an edge. A node dollar is incident to an edge if dollar is one of the two endpoints of that edge. It's about being attached.
Let me try a quick check. If I look at a single edge, that edge is incident to two specific nodes. And those two specific nodes are adjacent to each other. Is there ever a situation where a node could be adjacent to an edge?
That's a great clarifying question, and the answer is no, not in the formal language of graph theory. Adjacency is strictly node to node, incidence is strictly node to edge. Keeping those terms distinct is key to avoiding confusion when we start working with algorithms.
Okay, so for this deep dive, we're focusing on a very specific kind of graph, the simple graph. We have to set some rules to keep our structures clean. What are the rules of simplicity that define the graphs we're studying today?
A graph is simple if it adheres to two core constraints. First, there are no loops. An edge must always connect two distinct vertices. You cannot have a self-loop from a node back to itself. Second, there are no multi-edges. You can have at most one edge between any pair of vertices $20. If you break either of those rules, you move into the territory of multigraphs or pseudographs. But simple graphs are the clean, standard model.
And since we said the definition of dollar implies no directionality, we are explicitly talking about undirected graphs.
That's right. Undirected means that if an edge exists between a $5, information or travel can flow freely in both directions. Think of it like a two-way street or a symmetric friendship. If we were dealing with directed graphs or digraphs, that symmetry is broken and the edge from $20 to $1 is distinct from $5. But today, we are in the realm of two-way, simple connections.
This brings us to a crucial, almost philosophical point that trips up visual thinkers, the visual trap. You could have two drawings laid out completely differently on a page, yet they represent the exact same structure.
This is critical to get your head around. The drawing is just a representation. You might twist, stretch, or rearrange the nodes in infinite ways. As long as the identity of the nodes and the list of which nodes are connected to, which remains absolutely identical, it is the same graph.
So the immediate takeaway for you listening is that structural identity is independent of spatial layout. The actual physical coordinates on a screen or a piece of paper are irrelevant.
Precisely. The blueprint is defined only by the underlying set of nodes, so $5, and the absolute list of connections, $80. If you can pick up the drawing of graph A and move the nodes around without cutting or adding any edges, and you end up with the drawing of graph B, they are structurally identical. Structure is identity.
Now that we have the language, let's meet the family. Our sources highlight 4 particularly prominent graph types that act as foundational building blocks for more complex networks. This is the graph zoo.
Right. These prototypes demonstrate key characteristics that we use to analyze any system. Understanding these 4 types gives you benchmarks for density, flow, and architecture. First, we have the most dense. The complete graph, $0. If you have $0 vertices, the rule is simple. Every single node is connected to every single other node.
This represents the theoretical maximum density for any network of $0 participants.
It does. It's the ceiling of connection possibility. You use $0 as a benchmark for comparison to measure how sparse or dense a real-world network is relative to the maximum possible connection. In a social context, it's a group where everyone knows everyone else, maximizing all the communication channels.
Okay, next is a structure defined by separation, the bipartite graph.
In a bipartite graph, the node set $5 is cleanly split into 2 disjoint groups. Let's call them $1 and $2. The defining characteristic is the connection rule. Edges only exist between the groups, never within a group.
This is where that dance class analogy comes back, right?
Exactly. Or think of dating apps or job markets. You have one set of entities, say people seeking jobs, that's $1, and another set, available jobs, $2s. The connections only happen across the groups. If you maximize that connection, linking every node in $1 to every node in $, you get the complete bipartite graph. Sit in $2, where men's is the size of the first group, and $s is the size of the second. These are essential for matching algorithms.
Our third member is the simplest visual structure, the circle graph, 7LR.
Yeah, $7 is just a ring structure. Nodes are simply strung together in a cycle. Each node has exactly 2 neighbors, defining the closed loop. This structure is often used to model simple ring topologies in networks or, cyclical processes.
And finally, one that might sound specialized but is deeply important for architecture and computation, the hypercube, QMeDLX.
The hypercube, 2 ateras in dollar dimensions, is a beautiful and highly efficient structure. Crucially, the nodes here are defined as length dollar bit sequences, so binary strings. If 2-4, you have nodes like 0000001, 1010, up to 1111. The connection rule is what matters. 2 nodes are connected if their bit sequences differ in exactly one position.
Wait, so the nodes are literally strings of 1s and 0s, and the connection is just 1 bit flip away?
That's it. And that constraint is so important because it relates directly back to coding theory. 2 nodes are connected if they have a Hamming distance of exactly 1. Hamming distance measures how many bits you have to flip to get from one sequence to the other. By requiring only a single bit flip for connection, you create an incredibly robust, highly parallel architecture.
Okay.
Data can be routed very efficiently across the hypercube because the paths are short and the structure is mathematically perfect. They're often used in parallel processing systems because communication between processors is fast and predictable.
That structural uniformity in the hypercube ties directly into the next central concept we must define: the degree of a vertex.
The degree of a vertex dollar, written as text dollar, is the simplest and most important metric in graph analysis. It is simply the count of how many edges are attached to that vertex.
So it's the measure of a node's immediate influence or its local connectivity.
Absolutely. If we return to the social network, your degree tells you instantly how many direct friends you have. If your degree is 50, you are highly connected. If your degree is 1, you are almost isolated. This measure is fundamental for identifying hubs, central figures, or weak points in any network.
Before we move on, we should probably clarify the two related concepts you might encounter: the neighborhood and the cut.
Good point. The neighborhood, nolnaja, is simply the set of nodes connected directly to dollars, so the degree is just the size of that set. The cut, delta, is the set of edges incident to dollar. Again, the degree is the size of the cut. These concepts just formalize the immediate environment around a node.
And if every node in a graph shares the exact same level of connectivity, we call it a regular graph.
A graph is k-regular. If all vertices in the graph have the identical degree to dollars, these graphs are highly sought after in network design because they distribute the load evenly. There are no single points of massive traffic or failure.
Okay, let's apply this to our zoo examples. What's the regularity of the complete graph dollars?
Dollars is only regular. If you have nodes, you are connected to everyone else, which is only on long connections. Perfect uniformity at maximum density.
The circle graph.
$1 is too regular. In a circle, everyone has exactly 2 neighbors, which maintains that loop structure.
And the hypercube.
Hypercube. The hypercube, Kudu-Kordu, is dollar regular. The dimension of the hypercube is its degree. Because the connection rule states you must differ in exactly one of dollar positions, every node must have exactly dollar neighbors. This inherent strong uniformity is why $2 is such an efficient and balanced architecture.
We've established that the degree is the measure of the individual node. But if we aggregate all those individual degrees across the entire graph, we uncover a profound, mathematically mandatory truth. It's about the relationship between nodes and edges, and it's known as the handshaking lemma.
This structural observation is truly foundational. It states that if you take the sum of all node degrees in a graph, so you add up the connectivity measure for every single vertex, that total number is exactly twice the total number of edges in the graph. So $2 times EO.
It seems obvious in retrospect, but it's deeply profound because it imposes a structural constraint on any network you can draw. Why? Why must the sum of degrees be precisely 2 EAS?
The proof is an elegant application of something called double counting. Imagine you are an accountant counting the connections in the network. When we calculate the sum of all the degrees, we are visiting every node and counting every connection that terminates there.
Okay, so every single edge has 2 ends.
Exactly. Consider one specific edge, let's call it P edge. This edge connects node dollars and node vi. When we calculate the degree of 2, we count EO once.
Then, when we calculate the degree of dollars, we count nil again. Since every edge is structurally defined as having 2 ends, when we sum up all the ends, which is what summing the degrees does, we must necessarily count every edge twice. It's a structural guarantee.
That makes the proof wonderfully straightforward. But what is the caveat? If we move to a scenario with loops or multi-edges graphs that are not simple, does the simple 2 EBA dollar rule still hold, or do we need to adjust the count?
That's a crucial technical distinction. If we introduce multi-edges, so multiple connections between 2 and L's, the rule holds perfectly because each distinct edge is still counted exactly twice. However, if we introduce a loop and edge from rollback to $1, that loop only has one endpoint associated with distinct nodes. In most conventions, a loop contributes 2 to the degree of node del, but it is still only one edge. So for multigraphs with loops, we have to be careful with the definition of degree. But for our simple loop-free graphs, the sum of degrees equals 2HL is a perfect, clean equality. Now for the famous consequence. Because the total sum of degrees, $, is always an even number, this forces a highly counterintuitive structural result known as the party analogy.
Yes, this consequence is the one people remember. In any graph, there must be an even number of vertices that have an odd degree.
So at any party, the number of people who shook an odd number of hands must always be even. It sounds like a fun mental puzzle, but it's a structural necessity derived directly from the double counting principle.
Let's trace the logic. We know the total sum of degrees, cellulars, is even. We can split all the nodes in the graph into two groups. Those with an even degree, let's say even, and those with an odd degree, $5. The total sum dollar is the sum of the degrees in veg plus the sum of the degrees in Vaven.
And the sum secant must be even, right? Because any number of even numbers added together always results in an even number.
Exactly. Since the total sum dollars must be even, and Savan is already even, it mathematically forces Sybeth the sum of all the odd degrees to also be even. Because even plus even equals even.
And here's the kicker. How do you get an even total when you are only adding up odd numbers?
You can only achieve an even sum by adding an even quantity of odd numbers. If you have one odd number, the sum is odd. If you have three odd numbers, the sum is odd. If you have 2, 4, 6, or any even quantity of odd numbers, the sum is even. Therefore, the count of nodes in Vive must be even.
That's fantastic. It's the ultimate structural constraint. The nodes with the odd number of connections must sort of pair up to maintain the fundamental truth that every handshake has two ends. This is a foundational insight that proves we cannot simply draw any random structure. The degrees must always adhere to this parity rule. We established early on that two graphs can look wildly different on paper but still be structurally the same. We need to formalize that structural equality, the concept of graph isomorphism. We're moving into the question, when are two graphs truly indistinguishable?
This is a deep dive into the identity of the network. We ignore labels, colors, layouts, everything. We are asking, does the underlying map of connections match perfectly, even if we rename the streets and houses?
And what is the formal mechanism for proving that equality? How do you do it?
Isomorphism requires a perfect, structure-preserving correspondence. We need to find a one-to-one mapping, usually called bilars, between the vertices of graph dollars and the vertices of graph dollars. This mapping acts as a universal dictionary that translates the names from one graph to the other.
A one-to-one mapping means every node in dollars has a unique partner in dollars and vice versa. It's a complete roster swap.
Precisely. But the mapping taller must satisfy the key criterion. Nodes Duran dollars are connected in Duran dollar if and only if their mapped counterparts are connected in Duran dollars. If a connection exists in the original structure, the translated connection must exist in the new one. If a connection is missing in the original, it must also be missing in the translated structure.
This means if graph dollars and graph dollars are isomorphic, they are literally the same network, just visualized or labeled differently. It really is a renaming operation that leaves the web of relationships intact.
The structure is perfectly preserved. The names are different. The drawing might be radically different. One could be a simple square. The other could be a stretched out kite shape. But the connectivity blueprint is identical.
Let's consider the classic visual contradiction. You often see graph dialers drawn neatly, like a house, and graph dialers drawn messily, sprawling across the page like a star. Visually, they seem to be two different entities.
They look different, but when you apply the formal mapping function, you realize they share the exact same set of connections. If you trace the edges, if node 1 is connected to 2, 3, and 4 in G, the mapped counterpart, say node K in G, must also be connected to its mapped partners, which would be 532 and 54 dollars. If you find that perfect translation, you have proven isomorphism.
So that proves two graphs can be the same despite appearance. But proving non-isomorphism, proving two graphs are not the same, is often the quickest test we run.
That's our structural shortcut. If two graphs and dollars are isomorphic, they must share all fundamental properties or invariants. They must have the same number of vertices, the same number of edges, and most reliably, the same degree sequence.
The degree sequence is the list of all node degrees, just in ascending or descending order.
Exactly. Look at a graph shower that is not isomorphic to dollars.
Yeah.
If you count the degrees in dollars, you might find, say, 3 nodes of degree 2 and 2 nodes of degree 3. If your jigglers have a different count, say only 1 node of degree 3, you can stop instantly. Because the degree sequences don't match up, you know for a fact that no matter how hard you try to rename the vertices, you can never create that perfect structure-preserving map.
So the degree sequence test is the first defense against false isomorphism. It's necessary for isomorphism to exist, but isn't sufficient. If two graphs have the exact same number of nodes, edges, and the same degree sequence, are they automatically isomorphic?
That's where the complexity deepens. No, the same degree sequence is necessary, but not sufficient. You can easily construct two graphs that have the same number of nodes, edges, and degrees, but where the internal organization of those connections differs. For example, in one graph, the high-degree nodes might be directly connected to each other, forming a central pore. In the other, those high-degree nodes might be separated by lower-degree nodes. They have the same components, but the wiring is different.
Which means you still have to go through the difficult task of finding that renaming function to Gallers.
Precisely. Isomorphism requires the perfect preservation of every relationship, and the simple degree check only captures a localized property. That's why the graph isomorphism problem, determining if two structures are identical, is such a difficult and fundamental computational challenge.
We've established the identity of graphs. Now let's look at how we modify them, break them down, or focus on specific parts. We start with subgraphs, which are defined by removing nodes and edges from a larger structure.
Subgraphs are essential because in real-world analysis, you rarely care about the massive structure as a whole. You often need to analyze a specific component, a cluster of servers, a specific clique in a social network, or a single component in a circuit.
But just like with isomorphism, there is a crucial and subtle distinction here that dictates how faithful the analysis will be. The difference between a weak subgraph and an induced subgraph.
This subtlety is critical for proper graph analysis. A weak subgraph is created by arbitrarily removing both nodes and edges. You select a subset of nodes, and then you selectively choose which edges between those nodes to keep and which to discard.
So it's a deliberate weakening of the structure. I've selected a set of actors, but I've chosen to ignore some of their existing relationships for my analysis.
Exactly. You are analyzing the structure but leaving out known links. This can be useful if, for example, you only want to study strong ties and deliberately ignore weak ties, but it doesn't faithfully represent the full connectivity of the chosen nodes.
Okay, so what's the difference then with an induced subgraph GV dollars? That sounds more constrained.
It is, and therefore often more powerful for structural analysis. For an induced subgraph, you start only by selecting a subset of nodes, $5. The absolute rule is that you must keep every single original edge that existed between those selected nodes in the original graph. You do not get to pick and choose the edges. The relationship structure is mandatory.
So if I select a group of people for analysis, and two of those people were married in the original network, they must be connected in the induced subgraph.
That's the core difference. The induced subgraph preserves the inherent complete relationship structure of the chosen subset. If you want to analyze cliques' fully connected groups in the original network, you look at the subgraph induced by those clique members because it faithfully maintains all their original interactions. Induced subgraphs are foundational to identifying structural properties like cliques where everyone is connected, or independent sets where nobody is connected.
That distinction, the freedom to weaken versus the mandatory preservation of relationships, is critical for structural integrity. Okay, moving beyond simply taking pieces out, let's cover the basic ways we can surgically manipulate the structure. These are the operations we perform on a graph to analyze change.
The simplest operations involve deletion and addition. First, deleting a node, via Dale. When you remove node followers, you must also remove all the edges incident to it. It's like removing an intersection and all the roads leading into it. Second, deleting an edge, $. You remove the specific connection dollars without affecting the nodes. This is often used to model network failures or broken links. And third, adding an edge plus $. You introduce a new connection between two existing nodes that were previously not adjacent. This model is establishing a new relationship or infrastructure link.
And then we have the advanced abstract move that fundamentally changes the topology. Edge contraction.
Edge contraction, denoted JMER, is a unique and powerful restructuring operation. You select an edge and imagine it shrinking until the two nodes, 6 and 9, fuse together. They merge into a single new supernode, which we often call Viber.
So the resulting graph loses one node and one edge compared to the original. But what happens to the connectivity? How does that new supernode integrate into the network?
The new supernode Viber must inherit all the former connections. So Vider connects to all the old neighbors of Zollers and all the old neighbors of Yair. If 6 and I shared a neighbor dollars, will now connect to Zier via a new multi-edge. Though in a simple graph context, we usually simplify that down to one edge.
What's the practical purpose of this simplification? Why would you want to contract an edge?
Contraction is not just visual merging. It is a critical step in many optimization and proof algorithms. It allows us to simplify complex networks while preserving core connectivity properties. For example, in problems like finding the minimum spanning tree, the cheapest way to connect all nodes contracting highly connected components speeds up the calculation because you've reduced a complex cluster to a single, easily manageable point. It's a tool for transforming a hard problem on a large graph into an easier problem on a smaller one.
We've established the theoretical structures. Now we pivot to the practical reality. How do we take this complex web of abstract connections and force it into the rigid, finite memory structure of a computer? The choice of storage dictates the speed and efficiency of every algorithm we run.
This is perhaps the most important architectural decision in applied graph theory. The storage method must balance two competing priorities: fast lookups versus minimal memory usage. Our sources outline three primary methods, starting with the matrix approaches, which prioritize speed.
Method A, the adjacency matrix.
The adjacency matrix is the clean, fast answer for small or dense graphs. If you have no nodes, you create an 1 times no matrix. The matrix acts as a quick reference grid. If no dollars are connected, you place a 1-0 at their intersection, year dollars. Otherwise, it's a zero bone.
And since we are dealing with undirected graphs, that matrix is always symmetric.
Correct. The connection from 5 to tom mirrors dollars, so the matrix is a perfect reflection across the main diagonal, so $1 is a $t. The massive computational advantage here is speed. Checking if any two specific nodes N or R are connected is instantaneous. Just look up AUVNEO, which is an O-non or lookup constant time, regardless of the size of the graph.
Method B, the incidence matrix. This involves edges, not just nodes, on one axis.
The incidence matrix offers a different perspective. We still have nodes as rows, but the columns now represent the edges. So $dollars no or no is no NOA if node dollars is an endpoint of edge NR and on or otherwise.
This matrix is very useful for verification, right?
Yes, because every column has a built-in constraint derived from the simple graph definition. Since every edge must have exactly 2 endpoints, every single column in the incidence matrix must contain exactly 2 ones. This provides a structured mathematical verification of the integrity of the dollar pairing.
These matrix methods are conceptually clean and incredibly fast for connectivity checks, but they come with a major computational drawback, especially as the graphs scale. What's the catch?
The major drawback is memory space. It's known as the dollar problem. Both matrices require memory proportional to the square of the number of vertices. If your graph has 1 million nodes, you need 1 trillion storage slots.
That is an impossible burden for any real-world large-scale system like Google Maps or Facebook.
And most of that memory is wasted because most real-world graphs are what we call sparse or thin. Sparsity means the number of edges is far, far smaller than the maximum possible number of edges. In a massive adjacency matrix for a sparse social network, nearly every entry is 0. You are effectively storing massive amounts of zeros just to enable that fast lookup speed. It's like having a giant phone book where only 1% of the lines are filled in.
So we need a method that respects the sparsity of real-world data and minimizes memory usage. This is where the standard solution for large networks comes in. Method C, the adjacency list.
The adjacency list is the practical solution adopted by virtually all modern systems dealing with large graphs. Instead of a giant $1 times union matrix, we use an array. And for every vertex, we simply store a linked list of its immediate neighbors.
So instead of 1 trillion zeros, node V$1 just stores the concise list. $2, V3, V5 free.
This is fantastically efficient in terms of memory. It only requires memory proportional to the number of vertices plus the number of edges, so lol OV plus E. For a sparse graph where Euler is small, this is a saving of several orders of magnitude compared to the dollar requirement of the matrix.
That's a huge win on space, but as you mentioned, there's always a trade-off: speed.
This is the classic computer science dilemma, space versus time. While the matrix allows for instantaneous all or lookup for adjacency, the list makes the adjacency check much slower. If you want to know if nodes or $2 are connected using an adjacency list, you now have to go to node dollars list and search through it sequentially to see if VIME is present. That takes time proportional to the degree of $2.
So if node goals is a major hub with thousands of connections, that list search takes much longer than the matrix lookup.
Exactly. So the choice is an architectural decision dictated by the algorithm. If you run an algorithm that needs to quickly check every potential pairing like dense graph analysis or checking the global structure, the matrix wins. If you run a pathfinding algorithm like Dijkstra's, where you only care about immediately accessible neighbors, the list structure dominates because you save huge amounts of memory, and those local lookups are still reasonably fast.
Understanding that memory speed trade-off is often the difference between a theoretical graph algorithm and a usable, scalable production system. We've covered the absolute bedrock of graph theory today, moving from abstract definitions to core computational realities. We established the foundational pair, the vertices and edges, and the rules of simplicity that define them. We learned the necessary structural constraint imposed by the handshaking lemma that the sum of degrees is always double the edges, forcing an even count of odd-degree nodes in any network.
And we elevated our understanding to identity, defining isomorphism as the ultimate structural equality, where we prove that two graphs are identical through a perfect renaming function, even if their visual appearance is deceiving. Finally, we explored the crucial computational reality, contrasting the space-intensive, fast lookup adjacency matrix with the space-efficient, list-based approach preferred for large-scale, sparse, real-world networks.
That structural identity, the renaming game, leaves us with a truly deep thought that touches on the limits of computation itself. We saw how quickly we can disprove isomorphism. Just check the degree sequences. But proving that two graphs are isomorphic requires finding that perfect, structure-preserving renaming function, that's Siddle-Baylor.
And this task, known as the graph isomorphism problem, is notoriously hard, especially for large, complex structures. It occupies a strange corner of computational complexity theory. Well, we don't know if it's NP-complete, meaning it's as hard as the hardest problems we know. We also don't know if there is a quick, efficient polynomial time algorithm to solve it. It's one of the great open challenges in computer science.
So what does this tell us? If we can define a structure perfectly, why is verifying its perfect twin so incredibly hard for a computer?
It suggests that simple structural verification is inherently far more complex than it appears. The difficulty of merely finding that translation map, that renaming function, highlights that the essence of information and uniqueness in complex data is not easily captured by current efficient algorithms. The very challenge of confirming sameness in these abstract structures skirts the boundary of computational efficiency, making graph theory a deep dive that continues to define the limits of what computers can rapidly solve.